So this is Bayesian analysis of linear contracts. My name is Tal, and this is based on joint work with Paul Duetting, Yingkai, and Inbal Talgam-Cohen. And the fundamental thing I'm going to be talking about is incentivizing effort in simple ways. So contract theory, and specifically the principal-agent model developed by Grossman-Hart, is the classic model to address issues of incentivizing effort. In this model, there is a principal, which can be thought of as a firm, and an agent, which can be thought of as an employee hired by the firm. The agent has the ability to choose from various actions, each of which has different impact on the principal. To simplify, we can think of the agent as being assigned with a specific task and can decide whether or not to invest effort in it, as well as the level of effort to exert. The principal seeks to influence the agent's choice, and this influence will often take the form of a contract in which the principal monetarily compensates the agent for his actions using payments. And the fundamental challenge in contract theory is known as moral hazard or hidden action, which captures the idea that the principal is typically not able to observe the agent's exact actions. Instead, the principal observes a stochastic outcome of the agent's action, which serves as a noisy indicator. And the primary objective is to identify the contract, the payments, that optimize the principal's revenue, which is the difference between the rewards derived from those outcomes and the payment made to the agent for those outcomes. In our work, we study a generalization of this problem, where on top of the fundamental information asymmetry of moral hazard or hidden action, there is also the information asymmetry of adverse selection or hidden type. And adverse selection means that agents have private information regarding their individual characteristics or type, which affects how they behave under the problem. For example, the employee can have private information on his specific working capabilities. And building upon our previous work, we study a model where the agent has a single-dimensional private type, his cost per unit of effort. And the cost for a given action is linear in both the type and the required effort level of the chosen action. So fixing an action, some effort level, the lower the cost, the easier it is for the agent to perform the task, which means that the agent is stronger and higher skilled. Now, the focus of classic theory is mostly on the design of optimal contracts that achieve the highest possible revenue for the principal. In practice, optimal contracts can be challenging since they may involve extensive analysis and computing complex, non-intuitive terms to the agent. In our model, we actually show that optimal contracts can have large many-size complexity, which basically means that the amount of information transferred from the principal to the agent in a straightforward communication of contract is large. Additionally, we show non-monotonicity of the revenue with respect to the type distribution. So when the type distribution is more concentrated on stronger types that are easier to incentivize, the revenue can sometimes be lower. And these properties are obviously undesirable in practice and motivate the study of simple contracts. One form of simple contracts commonly observed in practice is linear contracts, where the principal offers a fixed share of the rewards from the agent's action as a payment to the agent. So for example, when the agreed share is 1/2, then for a reward of $100, both the principal and the agent would receive $50 each. So we analyze the performance of linear contracts by employing the theory of approximation in Bayesian settings where the agent's private type is drawn from a publicly known distribution. Previous work by Duetting, Grafgard, and Talgam-Cohen have shown that linear contracts are not approximately optimal in the degenerated case of our model where the agent's type is known, or the distribution is point mass. We revealed that this is actually a critical boundary case, and linear contracts are approximately optimal when there is sufficient uncertainty regarding the agent's type, and the setting is therefore not point mass-like. So we give this condition, the small tail assumption. This is a condition on the principal agent instance, which basically separates settings with low uncertainty, point mass-like settings, from settings with sufficient uncertainty. And as a main result, we show that under this condition, linear contracts give a constant factor approximation to the optimal contracts. And without getting into too much details, This allows us to achieve the following result for special distributions such as normal, uniform, and distributions with non-decreasing densities such as exponential distribution. So before getting into the technical part, I want to talk about the connection to previous literature. There are three main streams of works that are most related to ours. First is the line of work on the justification of linear contracts from the perspective of robustness or maximum optimality in non-Bayesian models under many different assumptions. Our work also contributes to a broad literature on problems that combine moral hazard with adverse selection, both from economic and computational perspective. And lastly, this analysis of linear contracts using worst-case approximation is gaining traction and has been adopted in pure moral hazard setting by Duetting et al. And subsequently by Castiglione et al. And Guru-Ganesh et al. In Bayesian settings. Both have shown that in their models, which incorporate multi-parameter types and additional uncertainty on the uncertainty that we have in our model, linear contracts have suboptimal performance. So now I'm going to introduce a concrete model. So there is an agent and a principal. The agent has a set of available action. Each one is associated with a distribution over a set of rewards for the principal and the number of units of effort it requires. The agent's action is privately known to him, and the agent also has a privately known single dimensional type. C, also known as his cost, as this parameter captures the agent's cost per unit of effort. So when the agents take action I, his cost is gamma I times C, the amount of units of effort this action requires times the cost per unit of effort. We assume that types are drawn from a publicly known distribution G supported on C on the line to C bar. And as I mentioned earlier, to influence the agent's action, the principal sets forth a contract, which is a payment for pay every outcome. Since the agent can have different types, we allow the contract to depend on those types. So it is going to be consistent of two mappings. One is from the agent's type to recommended action, and the other is from the agent's type to a payment scheme. And this is actually the direct revelation notion of a menu of contract. And since the agent's type is hidden, we rely on the agent's type report, which obviously not necessarily based to type. And then based on that, the payment scheme and the action recommendation is determined. One class of contracts we are especially interested in is linear contracts, where the payment for every outcome is an alpha fraction of this outcome's reward. And given a contract, the agent chooses a type report C hat and an action that maximizes the expected payment minus cost. And the principal designs a contract that maximizes the expected reward minus payment to the agent, subject to the constraint that the agent is being truthful and following the recommended action. And the welfare of the contract obviously is the sum of both parties' utilities, so it is the expected reward minus cost. So now we can establish our main result, approximation guarantees for linear contract, arguably the simplest non-trivial class of contracts. So we first identify a crucial condition referred to as a small tail assumption, which separates the case of point mass-like settings from typical settings with sufficient uncertainty. So for kappa that can be thought of as a type within C underline and C bar, and eta a parameter in 0 to 1, an instance is kappa at a small tail if the welfare contribution from types greater than kappa is at least eta of the entire welfare. So this curve shows the welfare contribution of every type C, in gray in the entire welfare, and in orange is the welfare contribution of types above kappa. The kappa at a small tail assumption is satisfied if the orange area is at least eta of the gray area. Intuitively, the kappa at a small tail conditions quantifies how much of the welfare is concentrated around the lowest, the stronger type. The larger kappa and eta are, the higher the welfare concentration is on higher type, the smaller the tail, and the further away the setting is from being point mass. Now, our definition of type uncertainty is not only a property of the type distribution, but also of the principal agent setting itself. we find that this dependency on the entire principal agent instance, not just the type distribution, is necessary for excluding point mass behavior. To illustrate this, consider a contract instance where the agent's type is drawn from a uniform distribution in the range of 1 to 100, where in the traditional sense there is substantial uncertainty characterized by high entropy and large variance. If, however, for all types greater than 1 plus epsilon for some small constant epsilon, the instance is such that even if the entire reward is given to them, they will still not be willing to take any effort-intensive task, meaning that a positive welfare and a possibly positive revenue comes only from types within 1 to 1 plus epsilon, then the instance can effectively be reduced to the case where the agent's true type lies within 1 to 1 plus epsilon, which makes the setting equivalent in nature to a point mass setting where the agent's type is 1. And the small tail assumption derives the first approximation guarantee for linear contracts that is universal for all type distribution. So for quantile q in 0 to 1, we take c sub q to be the agent's cost that corresponds to this quantile. If for alpha and eta in 0 to 1, the c sub q over alpha at a small tail assumption is satisfied, meaning that at least eta of the welfare contribution comes from types that are greater than cq over alpha, then a linear contract with parameter alpha provides expected revenue that is at least 1 minus alpha eta q of the optimal welfare. And the main takeaway from this result is that in order to guarantee a constant factor approximation of linear contracts, it is sufficient to assume that the welfare is not concentrated on a single type, meaning it is sufficient to guarantee that the distribution is not point mass-like. And the proof of this bound utilizes the concept of being slowly increasing, which can be applied to any cumulative distribution function and effectively captures its rate of increase. We provide a parametric approximation factor for linear contract that depends on the slowly increasing parameters, assuming the small tail assumption, and the universal approximation that applies for all distribution and only relies on the small tail assumption can be derived by observing that any distribution is slowly increasing for some parameters. So as already mentioned, the slowly increasing condition captures the rate of increase of a cumulative distribution function, G. So for alpha and beta in 0 to 1 and some type kappa, a distribution is alpha, beta, kappa slowly increasing if when the cost increases by a factor of 1 over alpha from alpha c to c, then the cumulative distribution function should increase by at most factor of 1 over beta. Intuitively, the small tail assumption captures the spread of the type distribution. When alpha is smaller and beta is larger, the cumulative distribution function increases more slowly, and the distribution is spread out over a wider range. With this, we give the following parameterized approximation bound that relies on the slowly increasing condition and the small tail assumption. And I'm going to give a high-level informal proof idea of the approximation bound given slowly increasing. So we want to show that the revenue of a linear contract is bounded away by a constant factor from the optimal welfare. As a first step, we are going to show that the revenue of a linear contract is at least 1 minus alpha of the welfare of a linear contract. And this is very simple. The revenue of a linear contract is 1 minus alpha of the reward, and the welfare is at most the reward. So we have that. And once we have this, to show a constant separation of linear contracts revenue from the optimal welfare, it suffices to show a constant separation between the optimal welfare and the welfare of a linear contract, which is now going to be step 2. So consider the welfare contribution of each type to the optimal welfare, as in the following curve denoted by opt. The optimal expected welfare is going to be integrating over this area when considering the distribution over type. And the nice thing is that because of the linearity in type and cost in our model, there is a close relation between this curve and the curve of the welfare of a linear contract with parameter alpha. To see this, note that when the agent maximizes welfare, the chosen action is the one that maximizes the expected reward minus cost. When the agent is offered with a linear contract with parameter alpha, the chosen action is the one that maximizes an alpha fraction of the reward minus cost. Taking alpha out, we have that this is the same as maximizing welfare when the types are scaled by a factor of alpha. Therefore, the welfare of a linear contract is close to taking the optimal welfare curve and scaling it down on the x-axis by a factor of alpha. So it's going to be opt of C over alpha. And again, the expected welfare of a linear contract alpha is integrating over this area when considering the distribution over types. And since scaling the types by a factor of alpha affects the cumulative distribution function by at most factor of beta, by the slowly increasing condition, we have that the welfare of a linear contract is bounded away by at most beta of the optimal welfare. And this completes the proof. So just to wrap up, we have a model that combines adverse selection and moral hazard, where the adverse selection component is single dimensional. In this model, we have seen that linear contracts are good under sufficient uncertainty, captured by our small tail assumption, which complements the max-min justification of linear contracts. This is nice considering that optimal contracts have multiple issues in practice. And in the paper, we also consider the benchmark of revenue and give refined approximation results by moving to the virtual cost space, similar to the virtual value space for a mechanism design. There are obviously many interesting questions here we have yet to understand. Some include finding other justification for linear contracts on different models or besides max-min optimality or approximation, and also finding other forms of simple contracts that are close to optimal. Thank you.